Hi guys, today we're going to talk about an idea called continuity. Now, you can find these notes on page 70 in your notes packet. We are starting a new chapter today. It's all about continuity, and then we'll get into differentiation. So we're not going to talk about differentiability today. Now, don't mark this out in your notes packet because we are going to come back to this idea. But for today, we are only going to talk about continuity. Now, continuity, you probably have thought about this in maybe pre-cal before, or even a little bit in algebra 2, possibly. But the idea of a continuous function you may have defined informally as like a nice smooth curve that doesn't have any holes, it doesn't have any gaps, no asymptotes, just a nice function that keeps going. I'm writing no asymptotes, holes, and then it continues forever and ever in the right direction and forever and ever in the left direction. This right here is an informal definition of continuity. And so it's nice in pre-cal to use the informal definition. It's nice in algebra 2 to use the informal definition. But now that you guys know about limits, we'll use the formal definition of continuity. So the formal definition of continuity has 3 parts. Part number 1. And this is for if a function is continuous at a specific point. So that would be like me looking at this graph and saying, okay, maybe at -3, is this function continuous at -3? So continuity at a point has 3 parts. The first part is that the limit as x approaches c of f of x exists. Now, to remind you, for the limit as x approaches c, for that to exist, remember that the limit as x approaches c from the left of f of x has to be the same as the limit as x approaches some constant from the right. So the left and the right-hand limit have to be the same value in order for this whole limit to exist. So these two must be the same. Okay? Then part 2 is f of c exists. So this is meaning that there is a point. That point exists at c. And then is the limit equal to the point? So in other words, is the number you get on number 1, is that the same as the thing you get from number 2? So if that's all true, then we'll say that the function is continuous at some value of c. And then here's that right now, just a little bit more. So we have some examples. We're going to determine if the function is continuous at a given value of c. And if not, determine which of the 3 rules, now the 3 rules, it's talking about these rules up here, which of these 3 rules are violated. So, and it's a given value of c, so the given value would be the number here. Okay, so first of all, let's see, is a continuous. And you might look at this and be like, oh yeah, it's not continuous. But we need to use the formal definition, which means we need to look at all 3 parts. So part number 1, does the limit as x approaches 1 of, and it's called f of x, does the limit of f approaches, as x approaches 1 of f of x, does that exist? Well, let's look at the left. The limit as x approaches 1 from the left is this number. The limit as x approaches 1 from the right is a different number. So we'll say the limit as x approaches 1 of f of x, that does not exist. No. So since this limit as x approaches 1 doesn't even exist, then we'll say rule number 1 is violated, and we would say that this function is not continuous because the limit doesn't exist. All right, let's try this part B. And I think it will help if I give a value. Let's say this is equal to 1. All right, so let's check condition number 1 again. Does the limit as x approaches 1 of f of x, does that exist? Okay, well, if I check the limit from the left, the y values approach 1. The limit from the right, the y values approach 1. So since those are the same, the limit as x approaches 1 of f of x is 1. So the first rule is satisfied. That's good. It exists. The second rule is that f of this value, f of 1? Does that exist? Well, is there a y value when x is 1? There's no y value here. No y value anywhere. So f of 1 is undefined. So that second condition is broken. So since even though the first condition is met, the second condition is broken, so we can say that f of x is not continuous at x equals 1. All right, let's look at another example. This time we're given the value of 0. So let's check the first condition again. Condition number 1. Looks like they've given us the value of 0, so I want to check the limit as x approaches 0. And let me say that this is 2. I just think it makes it easier if there's numbers labeled here. Okay, so let's check the limit as x approaches 1 of f of x. Let's see, as x approaches, I'm sorry, not 1, x approaches 0. So as x approaches 0, so from the left, as the x values approach 0, the y values approach 2. From the right, as the x values approach 0, the y values also approach 2. So the limit as x approaches 0 of f of x is 2. First condition, check. Second condition, the second condition is that we actually have to figure out the value. What is the value of the function at whatever the limit was approaching? So does that exist? Well, when x is 0, there's a point on the graph right here at 2. So that exists. Yes. So far, so good. We've got 2 of the 3 conditions met. All right, the third condition. I'm going to use my sparkle ink here because it all hangs on this one. Is the limit as x approaches 0 of f of x, is that the same as f of 0? So in other words, is this number the same as that number? Oh, they're the same. Yes, so that's true. So since all 3 of those are true, we can say that f of x is continuous at x equals 0. Now, if you're like, I can just look at that graph and tell you if it's continuous. Yes, you can. Right now, you can. You can tell me if that's continuous or not. Yes, but you're not always going to be given a graph. We're just starting off with a graph right now, and then later you'll be given clues about a function, and you won't be able to look at the graph at all times. Sometimes things that trip people up are things like example F. So let's look at example F. So condition number 1, what is the limit as x approaches 2 of f of x? Okay, well, as x approaches 2, from the left side, the y values approach infinity. From the right side, the y values also approach infinity, so we would say infinity. The second condition, what is f of 2? No, there's no y values on here, so I'm going to say that's negative 2. So when x is 2, the y value is negative 2. Well, are these the same? No, they're not the same. So the third condition, the limit as x approaches 2 of f of x is not the same as f of 2. So we would say that f of x is not continuous at x equals 2. Okay? Now, you'll have some in Delta Math that look like this. So here's a Delta Math example. Use a definition of continuity to determine whether the function f of x graphed below is continuous at x equals negative 4. So I have to go to negative 4, and I have to use the definition of continuity. And Delta Math is going to force you to check all the conditions and then write an explanation. So let's check all the conditions. So condition number 1, what is the limit as x approaches negative 4 of f of x. Okay, so as x approaches negative 4 from the left, looks like I get a y value of 2. As x approaches negative 4 from the right, I get an x value or y value of 2. Those are both the same, so the limit is 2. Condition number 1, the limit exists. Check. Condition number 2, now I have to figure out what is the value of the function at x equals 4. So what is f of negative 4? Well, at negative 4, the y value is 0. That exists. That condition is met. The third condition is, are these two numbers the same? Is the limit as x approaches negative 4 of f of x, is that the same as f of negative 4? Is that the same? Probably already screaming at me right now. Are those the same? No, they are not the same. So since they're not the same, we'll say, no, not the same. So we will say that f of x is not continuous at x equals negative 4. And again, Delta Math is going to take you through all three of these arguments when you write your answer. So you can't just look at it every time. You do have to be able to use the whole definition of continuity. Now, there are different types of continuity. There are 3 different types that you need to be familiar with. One is called a removable discontinuity. Then there's something called a jump discontinuity. And then there's something called an infinite discontinuity. Okay, so a removable discontinuity looks like, oh, there's not one on this picture, but I will insert one here. So it looks like this. Whenever, let's say there was an open circle on this graph and then a point up here. So like the limit from the left and the limit from the right, the limit exists and the value exists, but they're not the same. So I'll highlight this portion. I'll say this right here is an example of a removable discontinuity. So the limit exists, the value exists, but they're not the same. Removable discontinuity right there. Then there's something called a jump discontinuity. Jump discontinuities are when the graph pretty much jumps from one value to another. So if you see like right here, the graph is going down, then all of a sudden it jumps up here. So this part is an example of a jump discontinuity. Then you're asked about something called infinite discontinuities. Infinite discontinuities happen whenever there's an asymptote involved. So this part of the graph, you see how there's an asymptote right there. Even though it's not labeled with a dotted line, you can see that one side of the graph approaches negative infinity and the other side of the graph approaches positive infinity. That portion right there would be referred to as an infinite discontinuity. Now, sometimes they do have different names. Sometimes the infinite discontinuities are also referred to as non-removable discontinuities, but for our purposes in the book and the Delta Math that we're using, these are the 3 vocabularies that you'll see, but just know that you might see them referred to as something else in other books or in other courses throughout. So that's what I have for identifying continuities. Come back for the next video and we'll talk about how to deal with formulas and when you don't have the graph.